discussion with Kevin Miller, who is a research scientist at Google DeepMind.
Bring this here?
Yeah.
Do I have to? Okay. Excited to be here representing a group we're calling Google DeepMind Neuroscience Lab to share with you some thoughts we have, which are, I think, related to agent-based modeling. I'm interested to see if you agree, and it's fun to see the connections to different sorts of work that are going to be presented here. I'm going to start with sort of like at a really high level how I think about agent-based modeling in neuroscience. Maybe this is taking too far of a step back, but I think it can be useful. We imagine the brain to be this thing that puts out behavior into the world and then sees stimuli back from the world. And our job as neuroscientists is to figure out like what mechanisms live inside this brain and how do they work. And when we use agents to do this, that means we're building a software agent to perform similar tasks to the brain. It's putting out behavior into maybe a simulated world and seeing stimuli back, and it's got mechanisms inside of it. We'd like to use those as a hypothesis about what's going on in the brain. And I think for this to be practical, there's really three things we need which pull hard against each other in different directions. And one of them is that the behavior needs to really match the real thing. If it doesn't act like the brain, then it's not a good model of the brain. It needs to have mechanisms inside of it that we actually understand. If it's just as mysterious as the brain, then we haven't made progress. And these things need to be like practically discoverable for situations that we care about. If it's impossible to build them, then we don't have them, and then that's no good. There's two really classic ways of going about this in the field. One that they call classic cognitive modeling, where this is an example of a model that for a task that combines reinforcement learning and perceptual decision making. The point is there's some like well understood set of computations that are happening. And these are interpretable by design because they start with the human idea. The first thing you do is think about how you think the brain might work and then code up your idea, which means you require an inspiration from somewhere. And then the next thing you do is find out that your idea doesn't quite match what is actually in the data, and then you try to fix it. And this process is a sort of difficult, iterative, manual process that, at least when I've done it, does not typically result in a model that like really fits all aspects of the data. You sort of stop because you're out of ideas and throw up your hands and decide it's good enough rather than because you're like confident that you've nailed it. On the other side, we have generic neural networks. You can take a recurrent neural network, which you use a universal function approximator. You can fit it to your data set. If your data set is big enough and you do that right, it will fit all aspects of your data set. You may need a big data set, but we have those in neuroscience more and more these days. And it needs some post hoc interpretation. Now you have to go and try to like pick it apart and find out what's inside of it. And there's a lot of people been doing this for a long time and with some success, and I think that work is awesome. When I've tried to do it, I've also found that it does not result in like complete satisfaction, that I understand everything that's going on inside of this network. I'm always worried there's some wiggle that I don't understand, and maybe that wiggle matters. So in this talk, I'm going to talk about three different attempts to kind of combine the merits of both of these approaches and more automatically discover things that are easier to interpret. The first of those is a thing we're calling hybrid RNNs for your generalized classic models by replacing bits of them with neural networks. The second is called disentangled RNNs. You have this interpretably encouraging structure and loss function, which we think identifies kind of concise dynamical systems. And this thing we call cog fun search, which is identifying models using large language models plus an evolutionary algorithm, and it identifies short computer programs that we're going to consider to be models. So the first of these are hybrid neural networks. This is work that's been pushed a lot by Maria Eckstein and others together with me. Here you're replacing components of the classic model with a neural network. So conceptually, you might have like the idea that A causes B causes choice and C causes D causes choice, and those might be things that are meaningful to you, but you might not want to have to write down what the causal relationship is between these, so you can fit that with a neural network. This has been applied to economic decision making in the beautiful paper from Tom Griffith's lab that you should check out if you're interested in this approach. And here we're going to try to generalize it to apply to the case of reinforcement learning, which is recurrent and has some sort of new challenges. So this starts, of course, with a large data set that we're going to try to fit. It's from a very classic reinforcement learning task. We're not trying to reinvent the wheel on the data set side. Specifically, people play this game where they press one of four. It's a bandit game where you press one of four keys on the keyboard and you get back a reward, and the reward magnitudes available drift slowly over time, and people pick what they want and try to get points. And they show these sort of interesting, fun eccentricities to their behavior that it's not immediately obvious how we should try to model. And Maria collected this online, and it's a big data set. The next thing that she did is try to identify the best classic model. Tasks like this have been studied for decades. You can go to the literature. You can find lots of models there. You can compare them to each other. Maria did this, and she found one that we then named best RL because it's the best of the RL models, and it's got a structure that looks like this. I won't walk you through exactly the structure, but it's got hopefully, obviously, like a simple looking RL type structure. You can compare best RL to a generic RNN, and you can find that the generic RNN is just wildly better at fitting the patterns of the data. This is 60, and this is like 67 points of normalized likelihood, which is like a vast difference in this modeling space. So that's a little bit humbling and worrying and motivates us to try to figure out why. One immediate thing you might do is try to generalize the best classic model. So inside of these circles are some equations. Maybe those equations are wrong, and maybe we can generalize it by replacing those equations with these universal function approximators to say we're going to now allow it to fit any equation inside of that circle, and maybe that's going to let it fit better. The answer to my surprise is actually it does not help at all. The accuracy of this thing is about the same as best RL at the beginning, and it's still way worse than the vanilla RNN. And so that lets us make kind of a cool conclusion, which is not only is this particular model wrong, but like the whole class of models defined by this cognitive architecture is wrong, because this can identify sort of any model with this shape that has any equation in that space. So then the next thing you're going to be motivated to do is go look for other architectures that might do better. Maria did a nice search over lots of architectures that are possible and found sort of the most constrained one that still fit well, and it's an architecture that looks like this. This one does have quality of fit similar to the generic RNN, so its dot is way up high over there. And one way to find out what's going on is just sort of inspect the modularity of it, and this architecture is profoundly not RL-like. If you're an RL expert, you know that RL models are sort of universally have got incrementally updated variables where things change kind of slowly over time. This one is not like that. These things just get set sort of like a slot-based memory that each one, when it gets picked, it gets hard reset. You can also try to interpret this by just inspecting these rules. Because it's modular and this thing is feed forward, you can like sweep its inputs and look at its outputs and make a nice plot that shows you this is what's going on inside of that network. And you can look at it and get some intuition of what's going on. And you can also look at the dynamics of its memory variables. And one of the things that seems to be true here is a combination of super short-term memory variables like these ones, and super long-term memory variables like these ones. And you might at least start waving your hands and asking about whether there are connections to constructs like working in episodic memory. And all of this is sort of possible because we started fitting more generic types of models to the data. That's it for hybrid RNNs for now. Next up are disentangled RNNs. These are using an idea which we got from visual autoencoders, is the idea of disentangling. These are visual autoencoders are models that process images and learn representations. And they have this sort of magical property that they often learn representations with a very small number of latent variables that correspond one-to-one with like the human semantically interpretable dimensions of variability in the image. And that's kind of magical because it's not, to my knowledge, like a super well-defined thing, but in practice, it means things like one of these latents tells you what is the horizontal position of the square, and another one tells you like, is the circle purple or is it red or is it blue? And they vary sort of parametrically with the features that people would want to describe the images with. So that's sort of magical. We'd like that for our cognitive models. How are we going to get it? The key ingredient is this thing called the information bottleneck, which is a noisy neural network connection. It's got an input, which is a number. It's got an output, which is a number that's a noisy sample from some distribution that depends on the input and on some parameters here. And the amount of noise is penalized. So you can think of this as like a toll road for information. If you want to send bits down this connection, you have to pay to send them. And so the only information that the network is going to send after it's converged is going to be useful for something, and that's going to help it learn good representations. It can also effectively prune a connection entirely. You can say like sending information down this road is just too expensive. It's not worth sending any. And then from the interpretability perspective, you can decide to ignore that connection from the network, and that helps understand what's going on. So the disentangled RNN is taking this thing and putting it into an RNN architecture. We have some target Y, that's like, what did the animal do? We have some output Y hat, that's like, what did the network think the animal was going to do? These things come from some neural network, which takes as input some latent variables. Where do latent variables come from? Well, they get passed forward through time via these information bottlenecks, and so it can try to disentangle them and choose how many it wants to use. How do they get updated through time? They each get updated by their own neural network update rule, which takes as input, optionally all of the others, and also some observations. That's like, what did the animal see? And these also go through bottlenecks. And so if the update rule for internal variable number 1 doesn't need to know about internal variable number 2, that bottleneck can close, and you'll be able to read that off the structure of the trained network. So let's try applying this to some data sets. This is a data set that I've been working on for a very long time, like as long as I've been a professional scientist, more or less. This is from rats doing a bandit task. Here they pick a thing on the left or a thing on the right. They get a reward or they don't. The reward probabilities drift around, and we would really like to know what's the algorithm that they use to solve this task. And there's a nice big data set. There's a well-fit classic cognitive model, which like I produced by just trying very hard for a very long time, and I feel pretty good about it. I feel like I'm probably not going to get much better by trying harder. And so I was distressed several years ago to learn that the LSTM actually fits much better. So like there's stuff here that I still haven't modeled, which is frustrating and motivating to try to build new interpretability tools. So we can fit the disentangled RNN to this data set, and we can sweep. There's a hyperparameter that controls the cost of sending information through the network. So you can make the information very expensive, and then the network will not use much of it and will adopt a quite simple model, which might not fit well. You can make it very cheap, and then the information will send lots of information. It might fit very well. It might even overfit. And so we have the ability to sweep that. That's this hyperparameter on the horizontal axis here. And we can see that there's some medium value where it fits both better. Zero is the performance of my model. Medium value where it fits better than my model and about as well as the LSTM. And then we have this sort of continuum of models that might also be interesting, of ones that are, one that's simpler than that one, but fits about as well as my model did, and then some ones that are even simpler. And we can inspect these things to try to get an idea what do they have to say about what the rat might be doing. Okay, so let's inspect them. We'll start with the simplest one because it's the easiest to understand. Here we've got trials are on the horizontal axis. These things, I should have said before, are left choices, right choices, and rewards and omissions. And there are 5 lines here, and those 5 lines are the 5 internal variables of the network, but this one has chosen to turn off 4 of them, so they're flat on the horizontal axis, and only use 1 of them, which is bouncing up and down in a quite fast way. We can inspect what the update rule is for that one, and it looks like it's doing some fast time scale win, stay, lose, switch pattern. It's like learning where the rewards have been recently and going towards them, and learning where you've chosen and not gotten a reward and going away from that. And that's like a very simple model that does a decent job of capturing some aspects of the rat data. It doesn't fit as well as most other models, but it is very, very simple. We can let this thing get one step more complicated, and what it pretty reliably finds is that thing as well, that thing still, but now a new latent that only cares about choice and is very slow in time scale. So this is like a very long time scale pattern that likes to keep doing what it's been doing in the past, and you can wave your hands at that and try to make connections to constructs like habits. And this model actually is the one that fits about as well as my model did, despite being simpler. Mine had 3 variables and it's got 2, and it's just using them a little bit differently. So that's pretty cool. And then the one that fits best of all adds a 3rd variable. It's got the reward seeking variable, it's got the habit variable, and it's got this very slow thing that's modulating both of them in a way that depends on reward and interacts with them. And I think has got some features in common with the critic of actor-critic reinforcement learning models, specifically like when there's been a lot of rewards recently, there's smaller updates from reward and bigger updates from omission. And this is like a completely reasonable cognitive structure. You can look at that and interpret it as a sensible strategy for doing the task. There's no model that I'm aware of that's fit quantitatively to tasks like this that has this feature. The model that I honestly trying hard for a long time came up with, never explored models with that feature. And so I think it counts as sort of a genuine discovery of a new sort of computation that can do the task and is perfectly interpretable, but at least was not discovered by human scientists, or at least was not discovered by me for this task. Okay, another cool thing about the disentangling RNNs is you can apply them sort of immediately to totally new types of data sets. So this is work that's been pushed by Kyle Levin with our group at DeepMind. And he took these networks and applied them to this totally different task, which is a sensory decision-making task. In rats, the rat fixates the nose and listens to clicks on the left and right, like click, 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 and then is rewarded for going to the side with more clicks. So you can put clicks into the network and choice out and ask what it's going to do. There's a very deep modeling tradition using drift diffusion models for tasks of this kind. Kyle found that the disentangled RNNs, on average, fit a little better than the drift diffusion models, which is interesting. And they fit similarly well to the LSTMs. That's not on here. And if you inspect them, they actually have a cognitive structure that looks a lot like the DDMs. If you're a decision-making aficionados, this green curve you can think of as the decision variable. It goes down when there are clicks on one side and up when there are clicks on the other side. The blue curve you can think of as representing there's a short-term sensory suppression effects, where clicks that come together in close in time interfere with one another. And this is basically the same cognitive structure as the drift diffusion model that's popular in the field. So I think this one says, in a data-driven way, discovered that these people actually have stumbled on the right model class, like unlike me in reinforcement learning models where we've stumbled on the wrong model class. So, good for them. Oh, and these are the update rules. It's not worth the time right now, but if you were to look back and forth between these, you could convince yourself that what I said about how to interpret those variables was true. Okay, so that's the disentangled RNNs. The last tool I want to talk to you about is our newest tool. I'm going to give it quite high level because Kim is giving a talk tomorrow in the Rethinking RL workshop. We'll be just about this tool. So if you think it's cool, I'd love to talk to you about it. And if you think it's cool, you should go see her talk as well. And this is work that Kim and Pablo and I have been jointly pushing together with a lot of partial support from a lot of other people at DeepMind. And this builds on the idea that cognitive models, when we write them as in this branch of neuroscience, we typically write them down as short computer programs. We don't write them as neural networks. And so it would be pretty cool if we could make machines that write computer programs for us and write models in the language we're used to writing now. There's this very cool tool that we didn't make. It comes from the DeepMind science team called FunSearch, which allows using LLMs to optimize computer programs for a particular objective function. And we have adapted it, and now we're calling it CogFunSearch, which is just applying this idea to discovering computational cognitive models. So the approach schematically works like this. You have some program, and you're going to ask whether it's a good model or not. You're going to score it against a data set based on whether it produces a good likelihood for that data set. You're going to put it into a program database along with its score. This is an evolutionary algorithm, so you're going to sample parent programs from the database to get to generate new little baby programs probabilistically based on their score. And the way you're going to do that is take the parent programs and put them into the LLM prompt. There's a prompt that says, here's a description of what you're trying to do. Here's a program. Here's another program. Make me another program. And it will make you another program, and then you'll score it and put it in the database. And the hope is that by turning the crank on this, good programs will slowly evolve and can surface new ideas about how to use programs to model your data set. So I have just a little. So okay, we have a little teaser on this. For details, go to Kim's talk. We apply this to large data sets from RL task, including the human data set that I showed you earlier and the rat data set that I showed you earlier, and this very cool similar reinforcement learning task in fruit flies that was collected by our collaborators at Genelia. We find that we can identify programs that outperform the best human model. So here 0 is the best human discovered model. Blue is the performance of our best program, and orange is the performance of a generic RNN. So we're outperforming human discovered models and coming at least close to RNNs for all of the data sets. And it has this really cool feature, which is kind of my favorite thing about it, which is that it produces a spectrum of different complexities. So you don't get one program, you get 100,000 programs or 1 million programs, you have a vast number of programs, and you can break them down based on how well they fit and on how complicated they are using different complexity scores. So you can find not only a program that fits better and is more complicated, but also programs that fit better and are equally complicated, or programs that fit the same and are simpler. And I think this whole sort of spectrum of complexity there involves stuff that's fun to look at and can surface new ideas. Yeah. Just to give you a general sense of what these things look like, this is the best model that was discovered for the fruit flies. It's maybe a little more complicated than the model you would write, but it's not atrocious. It's not 1,000 lines long. And also, if you spent some time sitting and looking at it, believe me, you would understand what's going on. And if you want to do that together during coffee, that'd be a fun exercise. So it's got 24 lines of mostly readable code. It names its variables in informative ways. It writes comments. It has evolved some mechanisms that are completely reasonable, but don't occur in any model that I'm aware of for tasks of this kind, which is cool. And it has some remaining code quality issues. It has lines that do nothing, and sometimes it has variable names that are informative but misleading. This variable does not do anything like P choice. And so we've got some work to do, refining this thing. But I think it's already pretty cool and pretty useful. I want to close with something which I think is probably in this crowd not going to be at all controversial, which is we should be trying to do more interpretable data-driven discovery. In neuroscience, we've got technologies for collecting vast, rich data sets. including human behavior and animal behavior like I've showed you, but also including neural recordings and neural anatomy, just like explosion of quality and volume of data that's available, but have not yet resulted in like a complete understanding of the brain. In machine learning, we have amazing new technologies for learning things from vast, rich data sets. And so we should try to put these things together to learn neuroscience theories from data. And as we do it, we should maintain a commitment to interpretability, not just producing predictive models, because we can, but producing things that provide real insight into what's going on. And I think what interpretable means is interpretable to a human scientist is a useful mechanistic theory. In summary, I talked about agent-based models of behavior. They're a key tool in behavioral science. Neuroscience, we really need them. The existing methods for making them have some real challenges. Classic models are interpretable but don't fit that well. Neural networks fit really well but can be hard to interpret. Talked about 3 methods that might provide a different trade-off: hybrid RNNs, disentangled RNNs, and cog fun search. I want to briefly say that a lot of this stuff is available on GitHub if you want to try it, including code and data sets. We have a Colab tutorial. If you want to try any of this stuff, we would love to talk to you about it. And I want to thank my collaborators, including awesome people from DeepMind, Maria, Kim, Pablo, Kyle, and many others, and our friends at Genelia who were involved in developing a lot of these ideas and collected the Fruitfly data set. Thanks very much. You were first, and then you. Mm-hmm.
Seems like it didn't happen.
Mm-hmm.
Why do you think this is happening? And number 2, do you think there will come a day where set-setting models doesn't exist?
Yeah, I think this is an empirical question. I think we should find out by getting better and better at discovering models and seeing what we can do. I think the tasks we consider here are pretty simple. Like, we started with these because we thought if we can't discover interpretable models for this, then we'll never discover interpretable models for crazier things. And I think that we also need to think about how to be clever about regularizing them to be human interpretable. Like the fun search, the program synthesis approach, we ended up not needing to regularize it at all. Its only prior is like it learned to write code by reading human code, and so it writes reasonable code most of the time. But if we wanted it to write things that are 1,000 lines long, but nevertheless we can read them, I think we're going to need to coach it a little bit more and think about how to push it into this, express our ideas about what is and isn't interpretable in a way that like usefully interacts with the optimization process. And I think we don't know how to do that, but we can learn. Yeah, you absolutely can. I think that's the thing that's exciting about the approach is like these things are not only machine writable, but machine readable. I've dabbled with it a little bit, and my first things have not worked that well. But in principle, you absolutely can say like, hey, Gemini, please read all of these programs and tell me what they have in common that my models don't. And expect that if you put some energy into doing that right, you would get an answer that made sense, and other things like that.
Let's